All right, ladies and gentlemen, let's talk about probability. Are you ready? Okay. Jeremy, where are you? What's the answer to the first one? 1/2. I'm sorry, they changed the value of that they changed the value of pi recently to 3.1, and they have changed the value of the probability on a fair coin to 1 over pi. It's the coin, it's a round coin, so no, it's 1/2. Good job. Okay. I mean, because this is also established by a vote as well. By, like, people decide and that changes, whether it's 1/2 or whatever. So you'd have to keep checking. They might have changed it. They might, yeah. Like, check back with me tomorrow, okay, whether that's still a half. Good job, Jeremy. Haley, can you answer the second one? 1/4. And better yet, can you justify it? Okay, yeah, that's a nice analysis. There are 4 different outcomes. I like that. And for C, drawing a queen from the standard deck. How about Kate? Where is she? There. 1/13. Yes, or 4 out of, also known as 4 out of 52. I like it. Okay. Any comments so far? Anyone? All right. And then George. Do you think you know the last one? This is now they're getting a little tricky.
Wow, he does it. 1/12.
1/12? How do you come up with that?
Magic.
Good answer. Magic. Okay. Does anyone else agree with them or disagree? 1/12. Do you like that? Daniel? Agreed? Agreed?
Why is it 1/12?
I don't know. We'll write 1/12 and we'll talk about how to explain that later maybe. I don't know. We'll see. Maybe that's right. Maybe it's not. All right. I know there are questions that you might still have on homework, but we're gonna move on. We want to get through as much probability as we can today. The homework solutions will be online, I promise. And there are a couple of proofs that might have been tricky for you, but I believe in you. Okay. Okay. By the way, I feel good about saying to asking you probability questions, calling on anyone, whoever I like, because it's obvious to me, and you just proved it, that you have a little bit of familiarity with probability already. I'm trying to think when you encountered it besides AP Stat. Middle school or something? Elementary school. Yes.
Pulling stuff out of a bag.
Yeah, you're pulling things out of a bag in elementary school, right? Whatever. So I know that all of us have like either a life experience or some mathematical school experiences that have like brought you to a place where you have a little bit of an understanding about probability. All right. So the easiest thing to talk about first is probability for equally likely outcomes. So that's where we'll start. And I apologize. I really should on this slide have a couple other things defined here. An event. We're going to talk about the word event here. If E is an event in a sample space S of equally likely outcomes, then the probability of the event E is, well, I'll wait to say what that is in a second. But by an event E, we mean a set of desired outcomes. All right, so this is E and S are sets in like the set theoretic way, right? You know, you've thought about sets in your life before. E is the set of desired outcomes. That is, you're rolling a die, and the event maybe is rolling an odd number. So what kind of outcomes are inside that set? 1, 3, and 5, right, are the outcomes in the event E. And S we call the sample space, but that's just, again, that's another set in like the proper sense of the word set. And that's the set of all outcomes, right? So I should have that like come up on the slide, but there we go. Now we're good. So it's in fact okay to say, because again, these are sets. You could even say, right, the event E of desired outcomes is a subset of the sample space. Have you seen that subset symbol before? Right. So E is like a small part of S. And the probability, if all outcomes in S are equally likely, the probability is, of course, just the fraction that you've thought about before. It's, in fact, the way that Haley explained herself on part B of the warm-up today, right? You said there are 4 equally likely outcomes. She didn't say that, but that was implied by what she was saying. It's how some of you also thought about the other parts, too. You know, there are 52 equally likely outcomes, and 4 of them are desired. I forget who did the clean one, but that's how you read it. You said there are 4 equally likely outcomes that I want out of 52 total likely outcomes, so it's 4 out of 52. So that's how you reasoned on a couple of different problems. So I know this is intuitive to you. But what we can do is give you like really, really hard probability problems now, like right away, like immediately. This is like a non-trivial probability question. But the reason that we can give it to you right now is that both of these, the numerator and the denominator, are just counting problems, right? Like we've done a lot of combinatorics. We've laid a really good foundation for you. Now we can ask all sorts of hard probability questions like this one. How many outcomes are possible? Let's do the denominator first. How many 5-card hands are there? How do we compute it? Yeah. Close, but except that accounts for order, right? Divided by 24, which is 120, yeah. AKA 52, choose 5. But actually, I like the fact that you re-derived the definition of combinations on the fly. That was really nice, right? Isn't that what you just did? You said it's...
Is that wrong?
I mean, it's 52, choose 4. 52, choose 5. The definition of that is 52 times 51 times 50 times 50, 49 times 48. That go far enough. Times 40. Yeah, that's it. And then divided by 20, 5 factorial, right? To account for the fact that you didn't include order. I just want to make sure you like understand what you did, and that's exactly what 52 choose 5 does. That's the definition of the combination. How many cards have all 4 aces? How many 5-card hands have all 4 aces? If you take the deck, what would you actually physically do? You take the deck, you sort through it, and find the aces. You pull them out and put them in your hand, and then you have what task left?
48 left.
You'd have 48, and you have to choose 1. So you could write 48, choose 1, or you could just know in your head that you have how many options for that last card. It's 48 is what 48, choose 1 is. You don't have to write 48, choose 1 if you don't want. But do you see how like we can ask like kind of non-trivial questions? We can ask even harder questions than this too, right? Like what's the probability in a 5-card hand of getting at least 3 threes or something like that, right? You could, and then you have like the numerator would become complicated. You have right? We can ask some interesting questions though.
I don't really get what the numerator is for 48 is.
So in your hand, I'm forcing you to have 4 aces. So really, have I given you a lot of options? The answer is no, I haven't really. Your only option is to fill a 1-card slot in your hand.
Oh.
And how many things can you put in it? And the answer is 48. So there are 48. Like that's so few that we can actually show you all of the 5-card hands that have 4 aces. Like it wouldn't be hard to construct them. Right? It would take less than a minute if I showed you one hand a second. And then I don't know, 52 choose 5 is large. I'll have it there for you in a minute. We've seen this number before though, it's not news to us. I mean, in the end, the probability here is close to 0, right? It turns out that that's perfectly divisible by 48. That's nice. Anyway, so the idea here is that if you every 54,000 hands you see, I think we probably expect to see one that has 4 aces, right? On average. Okay. That's a lot of hands. So that's a powerful technique. And the reason it's powerful is because you know a lot about combinatorics already, and everything you know about combinatorics now rushes in to help you. Okay, what about unequally likely outcomes? Unequally likely outcomes we could talk about too. It's just that now for each outcome in the sample space, we weight it with some probability. For each outcome, we assign it a probability according to some distribution function. And so now we should say what a probability mass function is, a probability distribution function. My favorite word for this is a PMF, a probability mass function. But in AP Stat, you could probably call it a probability distribution function. Your calculator uses PEF as well. But PMF is the best word for it. Anyway, a function P, that is, this is what I promised would happen up here, right? Assigns each outcome to a probability. Okay? Imagine like a weighted die, where the probabilities are not for each face 1/6. Can you imagine that? So what are they? Will you tell me? For the number 1, assign a probability, please. For number 2, for the face that has 2 dots on it, assign a probability, please. What are you doing? You're giving me a probability distribution on the die, aren't you? It's not equally likely. That's all we're saying. That's all we're saying. And of course, you can't just arbitrarily assign to each face of a die a probability. You better give me numbers that make sense, first of all, as probabilities. Like, you can't be like, well, the probability of rolling a 4, I'd like that to be negative 1.5. It doesn't make sense, right? We require that these numbers be probabilities. And then, of course, we also require that, like, when you're done, that the 6 probabilities you give me for the die add up to 1, right? Otherwise, that doesn't make sense either. I'd like all of them to be 1/6, but one of the sides I want to come up 50% of the time, actually. No. So here's an example of an explicit function giving a PDF, or is it? We should see if this is a PDF. Just to be clear on the notation here, by P of capital X equals X, I'm saying what's the probability that the random variable X takes on one of these values, 1, 2, 3, 4, 5. So, for example, we claim that the probability of the random variable X being 2 is equal to 2 squared over 62. That is, I claim, this is what this is saying, that we're assigning the outcome 2 to the probability for 60 seconds, right? So the question is, is this reasonable? Keep in mind the function, but also the numbers over here are equally important. Sometimes this is called the support of the distribution right here. And it's super important too. Those are the only values X can be. It's the set of outcomes, the support of the distribution, okay? So, do they obey the rules up here? By the way, there's actually a third rule too that I didn't mention, but it's for another time, another place. We don't have to worry about it. Yeah. Yeah, so we should maybe stop and say what a random variable is. A random variable, we usually use capital letters, is a function that takes your set of outcomes and assigns to it a number. So in this case, what's the probability that we get 2, that our random variable X equals 2? That'll become more clear even on the next slide when I define a random variable for you. And I don't think I have the definition up there, but we'll define one in practice, and you'll see. So I know this is kind of a weird notation, but that's the notation that we like. So you'll get used to this, and we'll say more about it soon. But so is it pretty clear that all the probabilities are less than 1? Just by inspection, like if we plug in 5 to the 2 to the 5 to the 5th, I think we'll be okay. So then the only other thing we maybe want to check is the second criteria here. Is it true that the probability of our random variable being 1 plus the probability of our random variable being 2 plus all the way up to the probability of our variable being 5, does that equal 1 is the question. Did you check?
Yeah.
Does it work? It is 1? I didn't actually check.
Yeah. No.
20.
No, it isn't. Yeah, it is.
I think we're okay. Yeah.
For the thing that said P x equals x 2x over 62, it was something what
Yeah.
if it's 62 to the power of what? I can't read it. It's a comma. Okay. Never mind.
Oh, yeah. Here you mean. That's a comma. Yeah.
Cool.
All right. So, and then just a disclaimer here too. A PDF is given right here as an actual function, right? But in practice, oftentimes we won't have an actual function rule, but we'll have maybe we'll have a table or we'll have some other thing that assigns probabilities somehow, right? But it is cool that we can have a function. And keep in mind that like the function and, like I said, the set of outcomes is important. We need to have both there in order for this to make sense. So let's work out the probability. This is like part D on the warm-up today. Let's work out the probability distribution for the sum of two six-sided dice. And so I'd like to I should have said this somewhere here, but let's let the random variable x be the sum. So this is what we mean by random variable too. We mean like take the set of outcomes, and then the random variable x is the sum, and it could be various things assigned from the set of outcomes, right? So what is even possible for the random variable to have as its value if we have two dice? Could definitely be 8 or 9. What else can it be? Could be 10 or 11, the sum of two dice. What else? Anything between what and what? 2 and 12, and of course we're talking about integers, so hopefully I set my table up here correctly. Look at that, okay. So those are the set of possible outcomes, and now we need to figure out what's the probability of each of those things occurring. What is the probability of like rolling 2? That is the sum of 2. Yeah, here's some right answers. How are you computing it? 1 out of, what'd you say? 36. I think I agree with that. Can you explain though, Sam?
So to roll a 2, you have to roll a double 1, which means you have to. There's a 1 in 6 chance of rolling 1 on each die. So
Okay.
imagine you roll the first die. There's a 1 in 6 chance you roll that.
We have a nice picture of that here.
And
Yeah.
then you roll your second die. There's a 1 in 6 chance that you roll a 1 again. And so for every possibility of what you roll the first die, there are 6 possibilities for the second die.
Yeah, I like that.
Think about it. So you have 6 times 6 possibilities total.
So,
Remember what you want.
yeah, I mean, there is a way of maybe transforming this into the situation where you have like some equally likely outcomes to look at. These outcomes are not going to be equally likely, but one way to maybe think about this, if you've seen this before, I don't know, is to maybe list these out here, and here's a nice way to do that. Here's the result on one die, 1, 2, 3, 4, 5, 6. Here's the result on another die. And then I'm going to make like ordered pairs here, right? This represents like all the different things that could possibly happen in this situation, right? On the first die we could get a 1, and on the second die we could get a 1. On the first die we could get a 1, and the second one we could get a 2, etc. So there's the set of outcomes for us getting a 1 on the first die and something else on the other die. And then you could continue to make this if you like. Etc. Yeah, right? Etc. All right, and then all the way down here we have like 6, 6. Now, am I right that like every single possible thing that could happen with this dice is definitely captured in this table? Because we have all the outcomes on one and all the outcomes on the other, and we've like kind of we've written them out. So all right, now I'm ready to answer the next questions here. What about 3? Or yeah, the probability of getting a sum of 3.
2.
Yeah.
And it's like a curve.
What about 4?
3.
Oh, I see. I mean, we can just look at the table and look at them. I can see them. There they are. 2, 2, 1, 3, and 3, 1. Right.
Wait, but can you get 2 and
4,
1
5,
and
6,
the other?
and then it goes back down.
All right, and then
4, 5, 6.
5 is 436. Is that what you're saying?
Yeah.
I like this. It looks like there's a pattern.
And then it goes back down. 4 goes 6, 36, and then it goes back down.
All right, I was gonna go 7 out of 36.
No,
8.
you can't do that.
Oh, I can't do that.
because you're losing the 1, and then you're losing the 2.
So let's write this, but then we gotta come back through and make sure that makes sense. I see what you're saying. I definitely like 12 because in my mind, of course, 12 is equally likely as 2 because rolling 2 1s should be equally likely to rolling 2 6s. And if you go back to the picture here that we were drawing over here, we can highlight this nicely. Right there's the us getting 2. There's us getting 3. There's us getting 4. There's us getting 5. 1, 2, 3, 4. What's that?
Isn't it like the choosing thing? Like if you get, it's like the thing we did. Like 12 choose 1 would be the thing. 12 choose 11.
Yeah, I agree there's some nice symmetry here, but I think you'd be hard pressed to come up with like some rules for this. For this one, I think you might be able to do it. It's tricky. There's a nice trend to it, but as soon as we jump to like 3 dice, it becomes like an incredibly hard math problem. 4 dice, incredibly hard math problems, which I happen to know the answer to because I've thought about it before. But like it's like hard to come up with. All right, so.
3 dice, could you do like a 3-dimensional?
Yeah, you'd have to do a 3-dimensional picture like this, and then 4 you have to have like a 4-dimensional picture. Yeah, right.
How do you do it?
Or maybe there's another way to the solution, right? I don't know. Okay. You could use a computer, I guess. True. Anyway, so something for you to think about. Is this a good distribution, by the way? Does it add up to 1? Does it add up to 1? All right, hey guys. All right, so 36 outcomes maybe in this picture over here. Over here, our random variable x we only have what is that? 10, 12, 11 outcomes. Great. Then also calculate the probability of rolling a sum greater than 8. That's easy. Now that we have this table, right? This was the fun part. Now we're just adding up these probabilities, and this is what was meant earlier on. Like, how do we compute probabilities of unequally likely outcomes? And the answer is we have to just sum their probabilities from whatever the distribution is. So if we add those up, we get what do we get? Looks like we get, is that 10 out of 36? Yeah, so 5/18. All right. And there are lots of other cool questions you could ask, like what's the probability that the sum on 2 dice will be a prime number? Or what's the probability that the sum will be whatever, anything you like. By the way, doing this problem we just did makes me think of playing this game. Have you anyone played this game before?
Oh my gosh, yes.
What's it called? That's right. It's called Settlers in Catan. And it's fun. It's fun. I will say if you like this game, if you haven't played it, you should play it. But it is a gateway drug, okay? once you've learned this game, come and talk to me and I'll introduce you to some other complicated German board games that are really good. This is just the beginning, okay? But if you haven't played this game, allow me to zoom in a little bit and explain just a little piece of the rules. There's not a lot of the game I want to explain, but when you're playing this game, you build these settlements or cities around these tiles where you get resources from. And you get resources in this game whenever the number on the tile is rolled. So, and you have 2 dice in the game. So you could roll if a 10, the sum of the dice happens to be 10, then people on this tile up here with a 10 get resources. These people who live on the tile get that resource. Yay! Or, you know, if an 11 is rolled, then, so which in general, which tiles would be desirable to be on? Ones that have higher probabilities, obviously. Now they've helped you in this game by putting some dots on here. What do the dots mean? What do the dots mean? Yeah, do you see how many dots are on? Like, why are there 2 dots on the 11, for example? They're giving you the probability out of 36 for each of those spaces for the layperson, right? Who maybe doesn't have the probability distribution on 2 dice memorized, right? Which is fair. They don't say out of 36, but next time you play this game, like, you should recognize as you're playing that in full view is the probability distribution for 2 dice, the sum on 2 dice. Okay, or if you ever learn, you'll remember what we said here. Okay, it's fun, right? It's cool that we see that right there. So we expect that this doesn't come up very often, right? Approximately 2 out of every 36 rolls we would be seeing it in 11, or 1 out of 18 rolls. What's that one up there? There's a 12 and it has 1 dot on it, right?
Now the rubber.
You should, yeah, there's more to the game than what I'm describing. You know, it might be true that there are reasons you might want to build somewhere else. Like, one of them would be that someone else is already on this better one, but there are other reasons too. All right, let's turn our attention to another problem. By the way, notice that we're always playing games, aren't we? It's always cards, it's always coins, stuff like that, right? And actually, there's a good reason for that. There's a good reason for that, and the reason is that's how probability was birthed, right? Like, the reason probability came onto the scene was people were playing games of chance and wanted to make money in particular, and wanted to analyze games. That's where probability originally kind of had its source. Obviously, it's much more broadly useful now, but so we like games is the point. All right, this time we're tossing a coin 3 times in succession, and the question is, how many heads could we possibly get? So I'm letting the random variable x be the number of heads that we get. Okay, so what kinds of outcomes can we even have? That is, what kind of values? What kind of values can x even take on? We can have how many heads? We can have as few as 0. Yeah. Say it again, Teo. I know it's exciting. Thanks, guys. All right. Now, of course, we want to figure out that was the easy part. That's the number of heads that are possible. And then the question, of course, is what is the probability of each of those things happening? So let's think that through. Similar to warm-up problem part B today, right? What's the probability? Let's start with 0 heads. How do we compute that, and what is it? Yeah.
1/8.
Why?
Because you have 3, you're going to toss the coin 3 times, and there's a 1 in 2 chance of getting heads for each coin toss.
So it's like tails, tails, tails. Okay.
Yeah, the 1 chance.
Or I mean, we could go back to, they're all equally, there are 8 possible set outcomes. Yeah. There's tails, tails, tails. There's tails, tails, heads. There's tails, head, tails. There's head, tail, tail. We could list them out. It's not very many. And one of them is tails, 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 and none of the others are. So we could just say 1 out of 8. The other way to think about that, why are there 8 outcomes, by the way? It's like the pizza problem. 2 times 2 times 2. Think about the pizza problem, right? Okay. I think I also just solved another one up here. Right? Down here, what's 3 heads? It's also 1/8. Okay. What about 1? How many ways are there to get exactly 1 head? That is I mean, we could just write them down. It's HTT, THT, or TTH, right? So 3/8. Now, on this last one here, you could either run through the logic again, or you could just be like, what goes here? What has to go here? Whatever isn't, I mean, it has to add up to 1, doesn't it? Okay. This is kind of a dumb little picture, but we'll do it. If you wanted to plot this, you might plot it like that. Okay. Notice, hey guys. Notice that it's not. A continuous curve necessarily. We have like discrete sets of values. It's not like the random variable x can take on values, all real values between 0 and 3. It's only these, like only 4 possible domain values if you want to think about what the function can take as values. And then we output things, but these are the only 4 values that you're like allowed to ask it about. Okay? And big challenge now. Big challenge. Can we come up with a function that describes this? I'll give you part of it just because that's the kind of guy I am. There you go. The denominator is 8, I think. You're welcome. What's the numerator? If you give me an x value like 2, I want to have something I can plug it into and get 3 and then over 8. So this is a counting problem. How did you do it? How did you determine how many different arrangements, or how many different, if we're looking for one head, for example, up here, how did you determine that it was 3? How did we do that? I mean, we just wrote them out maybe, but what we... How many ways? Let's see, there are 3 slots to fill, and we need to fill one of them with a head. So which one do we want to pick? I don't know. Or we have 3 slots, and we want to fill them with 2 heads or something. How many ways are there to do that? Yeah, in general, what is it going to be up top? Say it like you mean it, though, Amy. Yeah, 3 2's x. All right. By the way, what is 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3? It's 2 to the 3rd in the numerator, okay? So I think that will work if you add those up, it'll work. So that's a challenge, bonus problem right there. I don't know that I'd make you, I don't know. It's cool though. It's important that we also maybe say this though, right? X equals 0, 1, 2, 3 again. That's part of the deal. All right, you've already used this today, so I think you know it. But this is the probability, this is the multiplication rule for probability. We already kind of discussed a multiplication rule that was at play in combinatorics, and this one follows immediately from that if you think about the theory underneath this. I'm using a piece of notation that I think you're familiar with. What does that cap mean? That cap means what? Say it. Good guess. What does it mean?
Oh, A and B.
Also known as and, right? Right? The probability that A occurs and B simultaneously occurs is the probability of the 2 multiplied, provided that, this is big and key and important, and hopefully we'll tease this out in the coming days here, provided that they are independent. So we'll say a little more about what we mean by independent as we look at these 2 problems here. So this first problem, we've got 2 jars. It's always jars and marbles. In the first jar, we've got 40 black, 60 white. And in the second jar, we've got 20 white, 5 black. And the question is, we're going to put one hand in one and one hand in the other and pick one out. What's the probability we get a black? From both? that is, what's the probability of jar A equals black and jar B equals black? Is that a good way to write it? I don't know. So, if in fact they're independent, and by independent we'll say more about this as we go, but by independent we mean like if the outcome of one thing doesn't affect the outcome of the other at all, which I think is safe to assume here, even though it doesn't mention the word independent, because they're physically independent. Like there's no way that like, I'm not waiting for you to pick from jar B to figure out what the probability will be from my jar A. Like it's not gonna matter what you get. If you pull a white, I'm not gonna be like, oh, well that changes things. I'm pulling out a jar A and that matters. It doesn't matter, okay? So this is just the product of those two, of course. And that's something. What are those? 40 out of 100 times 5 out of 25. That's comes out to be something. All right. Actually comes out pretty nice, right? What is it? 2/25? All right, and then let me just say a word about the last one. Can I do it before the bell rings? This one here, and we have more. We'll do tomorrow, I promise. The probability of randomly selecting and ordering a Frosty is 0.2, and the probability of ordering a burger is 0.5. Assuming they're independent, what's the probability? Of course, it's the product, right? But notice on this one that I had to tell you this, right? If you didn't know this, there's no way. I don't know. Can we assume that they don't affect each other? All right, homework 6 tonight, please.